Hello everyone, welcome. In this video I have one integral for you, and it's this integral here. Now how do we approach it? Well, here is how we approach it. Let's capture the integral first. So it's the integral from 1 up to 5 of the square root of minus 1/4 of x squared plus 3/2 of x minus 5/4, and then we have dx. Now the approach would be to factorize the expression under the squared sign. That would be our starting point. So this is the same as the integral from 1 up to 5 of the square root of, you would agree with me that the common factor would be taken as a quarter, and if we take a quarter into that, you get x squared, and that will be minus, remember that. And then a quarter into that, if you agree with me, a quarter into 3/2, the answer is actually supposed to be positive 6x, obviously. And a quarter into that, the answer will be minus 5, and then we have dx outside. Now remember, the square root of a quarter times this, we can rewrite it as the integral of from 1 up to 5 of the square root of a quarter multiplied by the square root of minus x squared plus 6x minus 5, like so, dx. Now let's factorize this expression inside. First of all, square root of a quarter is half, and we can take it out because it's a constant, so we have half outside times the square root integral from 1 up to 5 of the square root of, watch how I'm going to write this one now. Factorizing, take the minus out, and then you have x squared minus 6x plus 5, and then we have dx. Nice. Now I'm going to have to complete the square of this expression here, taking us to our next page. So like I said, the next approach would be completing the square of that expression. How do we do it? Well, we're going to at this point, let x squared minus 6x plus some constant k be equal to, watch this, the square root of x squared is x, and then we're going to say plus some number a squared. Basically, if this is a perfect square, it can be written like that, a square of a bracketed expression. Now we have to expand the right hand side. Let me move back a little bit. So we have x squared minus 6x plus k, and this will be equal to, expanding this, it will be x squared plus 2ax, and then plus a squared. Now equating coefficients, you can see the x squared is taken care of, and then we're going to take 2a equate to minus 6, and obviously k must be equal to a squared. So 2a is equal to minus 6. Solving for a here, we get a equals minus 3, divided by 2 both sides. Bring it this side, where we have k is equal to a squared, and you agree with me that this will be equal to minus 3 actually, and we square it, and the answer is just 9. Right, now it means that this expression here, we can write, we will say therefore it means x squared minus 6x plus 9, remember k is 9. From here we can write this as we're here now, x, what is the value of a? Minus 3, and we square that. Right, now our integral, therefore this integral here can be transformed as follows. We're going to say therefore half, let me capture the integral 1 up to 5 of the square root of minus, open brackets, x squared minus 6x plus 5 dx will be equal to half the integral from 1 up to 5 of the square root of, watch how I change this one now, we have minus outside, and we have to say open brackets. Instead of having that, I'm going to have x squared minus 6x plus 9. But now notice, why am I saying plus 9? I want this expression in that space, but I don't want to change it, and I have 5 here. So what must I do then? I must subtract 4 from this one, so that I maintain the 5 there. So minus 4, like so. And then I have dx. Fantastic. Now moving forward, you'll see how we're going to change this one here. We'll have it replaced by that. Taking us to the next page. What are we saying now? What we're saying is the following. We're saying now what we have is that integral is the same as half of the integral from 1 up to 5 of the square root of, watch this, minus, and we're saying instead of having x squared minus 6 plus 9, we're going to have x minus 3, and we square that, and then minus 4, and then dx outside. Now we can remove the brackets, the square brackets. What do we have? We have 1 over 2 times the integral from 1 up to 5 of the square root of, watch this now, minus x minus 3 all squared plus 4. And then we have dx. Rewriting that expression under the square sign, we have half times the integral from 1 up to 5 of the square root of 4 minus x minus 3 all squared dx. At this point, I'm going to force 4 to be the common factor of this expression under the square sign. The reason is I want to have 1 here minus something squared, so that I can take advantage of sine substitution as far as trig is concerned. I'll show you how it works. So this is basically going to be 1 over 2 times the integral from 1 up to 5 of the square root of, like I told you, common factor 4. 4 into 4, 1, minus 4 into this expression, we have x minus 3 all squared all over 4, like so, and then we have dx. Fantastic. Now watch how I'm gonna rewrite, take 4 out, and obviously I have to take the square root. So we have 1 over 2 times the integral from 1 up to 5 of the square root of 4 times the square root of, watch how I'm gonna write this expression here. I'm gonna write it as 1 minus x minus 3 all over 2, and I square the whole of this, and then I say dx. You agree with me that if you remove these brackets, you're back there. Now what is square root of 4? It's 2. We can take it out, but remember there's half outside here, so the 2 cancel. And what do we have? We have the following now. Moving forward, what we have now is the following. We have that integral will be equal to 1 over 2 times square root of 4 is 2 times the integral from 1 up to 5 of the square root of, watch this now, 1 minus, and we have x minus 3 all over 2, the whole expression, squared dx. Nice. These cancel outside there, so we have the integral from 1 up to 5 of the square root of 1 minus, in brackets, x minus 3 all over 2 all squared dx. Nice. Now at this point, I'm going to take advantage of sine substitution. Whenever you have square root of 1 minus something squared, it's the sine substitution. Right. So what we're going to say now is we're going to let sine theta be equal to x minus 3 all over 2. Now the first equation we're going to obtain here is to solve for theta. So we're going to say theta is equal to, and as you can agree with me, sine inverse or arc sine of x minus 3 all over 2. That will be the first equation. Second equation will be obtained firstly by taking advantage of the fact that we can define theta by using a right angle triangle as follows. So if that is our theta, we know sine is basically the opposite side by definition of a hypotenuse. So the opposite side will be that, the hypotenuse will be 2. So opposite side, x minus 3, hypotenuse, opposite right angle, will be 2. And by using Pythagoras theorem, this side here is just going to be the square root of that squared, which is 4 minus that squared, which is x minus 3 all squared, like that. And so from here, at a later stage, we're going to need cosine. So how do you define cosine? It will be at the adjacent side over the hypotenuse side. So cosine of theta is going to be the square root of 4 minus x minus 3 all squared, and we're dividing this by 2. We'll need this at a later stage. But I want to focus on this equation again. This equation, let me move this one down. I want to focus, maybe I should recapture the equation I want to focus on. I want to focus on the equation sine of theta being equal to x minus 3 all over 2, which is this equation here, I want to differentiate both sides, but before I do that, I have to multiply by 2. So we have 2 sine of theta is equal to, on the right hand side, if you agree with me, this is what you have. Now I'm going to have to differentiate theta with respect to x. So derivative with respect to x of 2 sine theta, the answer must be equal to derivative with respect to x of x minus 3. On the left hand side, 2 is a constant, take it out. Derivative of sine is cosine, and then we have to say d theta dx. What do we have on the right hand side? Derivative of x with respect to x is 1. Derivative of minus 3 is 0, because minus 3 is a constant. Now multiply by dx both sides. You will agree with me that we get 2 cosine of theta d theta is equal to dx. Fantastic. Now if you look at this integral here, it can be transformed totally. I'm going to have sine theta here, and this expression changes to 2 cos theta d theta. I'm going to ignore the limits of integration for a moment, and then I'll get back to the limits at the end after completing evaluation of the integral. So we're going to say, therefore, if we're looking at the integral of the square root of 1 minus x minus 3 over 2 or squared dx, this must change to the integral of the square root of 1 minus sine squared of theta times 2 cos theta d theta. Remember that dx is that expression, and this expression here must be replaced by sine theta. Now if you would recall, this expression 1 minus sine squared theta just cos squared theta. So if we move to the next page, then what do we have now? We have the following. We have the following on the next page. We have the integral of the square root of cos squared theta times 2 cos of theta d theta. And obviously taking the positive square root, that cancels that. And what do you have? You have this being equal to the integral of cosine of theta times 2 cosine of theta d theta. Simplifying this, this is 2 integral of 2 cos squared of theta d theta. At this point, I need to remind you of double angle formula for cosine. So we say cosine of 2 theta has 3 expressions. The first one is cos squared of theta minus sine squared of theta. The second one is 2 cosine squared of theta minus 1. And the third one is 1 minus 2 sine squared of theta. Now, if you look at this expression here, it's that expression. So therefore, I need this equation here. So I'm going to say, therefore, cosine of 2 theta is actually 2 cosine squared of theta minus 1. Add 1 both sides, 1 plus cos 2 theta. The answer must be 2 cosine squared of theta. And this expression here is that one there. So I must have this replaced by that. Taking us to the next page, we are basically saying now, let me move this one down so you're able to see where we're coming from. So let me recapture the integral, because I think I have enough space here. So I'm going to say, therefore, the integral, which is the integral of 2 cos squared of theta d theta, must change to the integral of, watch this now, we have 1 plus cos of 2 theta, and then we have to say d theta, because that expression equals that, as you can see over here. I'm going to have to distribute the integral and d theta, and what I get is the integral of 1 d theta plus the integral of cos of 2 theta d theta. Now, if you have watched some of my videos, you'll agree with me that this is just theta, and we're saying plus the integral of cosine is sine, but we have 2 theta here, so we have to say sine of 2 theta all over 2. Now we have to use double angle formula for sine over here. We maintain this one, theta, plus the numerator there is 2 sine theta cosine of theta. I told you we're going to need cosine, but we have 2 there, so these cancel. And what do we have? We have theta plus sine of theta cosine of theta. Now we need to revert to our original variable. In order for us to do that, we need to go back to that triangle which I drew. Let me remind you. We need to go back to this triangle here. It's on page what? Let me just check the page where we're at. It's actually on page 4. Here we go. We have the expression for sine, and we have the expression for cosine, and we have the expression for theta. And therefore, let me keep this one here and bring this one here. Notice something now, that if you look at this expression here, we have theta plus sine theta cos theta. So I'm going to have to replace this, that, and that on our page 8. And hopefully to just finish this off now. On page 8, what do we have? On page 8, let me keep this one here, hold it in my left hand. So I'm saying basically now that that should be equal to, what is theta? What is theta? Theta is sine inverse of x minus 3 over 2. So we are saying sine inverse, or arcsine of x minus 3 over 2. And then we have plus sine theta, plus what is sine theta? Well, sine theta is x minus 3 over 2. So we have x minus 3 all over 2 times what is cosine of theta? And cosine of theta is this expression here, which is square root of 4 minus x minus 3 all squared all over 2. Fantastic. Now the whole integral is evaluated. We must move back now to consider the limits of integration. Where did we stop? Where did we leave out the limits of integration? The answer is over here. Remember, on page 4, I think. Page 4, yeah, here we go. This is the page where we said, let's ignore the limits of integration, and then we'll get back and use our limits. So now we're going to say this integral must change to that with the limits of integration added. So we're going to say, and if you allow me to just move to the original integral, because we see that this is coming from there, which is, if you like, from the original integral, which is this one here, which is, must go to page, there you go. So I'm gonna now say that this integral here must be equal to this expression evaluated from 1 up to 5. So the conclusion is, therefore, the integral from 1 up to 5 of the square root of minus a quarter of x squared plus 3 over 2 x, and then minus 5 over 4 dx, this must just be equal to sine inverse of x minus 3 over 2 evaluated from 1 up to 5 plus x minus 3 over 2 in brackets times the square root of 4 minus x minus 3 all squared all over 2, and we're evaluating from 1 up to 5 as well. Right, I'm going to move back a little bit so that you can see that clearly. Now, moving back, what is this? This is sine inverse of 5 minus 3 over 2 minus, remember we have to put 5 there and then 1 and then subtract. Sine inverse of 1 minus 3 over 2, and then we're going to say plus. Now this part here I'm going to have to write it over here because of space, and I'm substituting 5. Remember the upper limit is 5. So 5 minus 3 all over 2 in brackets times the square root of 4 minus 5 minus 3 all squared all over 2, and then minus, I'm going to substitute 1 now, and I'm coming back there 1 minus 3 all over 2 in brackets times the square root of 4 minus 1 minus 3 all squared and all over 2. Fantastic. Now watch something here. This is gonna be 4 there, because 5 minus 3 is 2, squared is 4. This collapses, and the same story here. Minus 2 squared is 4. From 4 is 0. Square root of 0 is 0. So the whole of this collapses. So that gives us 0, and that one also gives us 0. We are back here. So we're saying basically that this simply gives us the sine inverse of minus 1, positive 1 firstly here, because that will be 2 over 2 is 1, minus sine inverse of minus 1, because that's, if you check, minus 2 over 2 is minus 1, minus sine inverse of that. Now what does this simplify to? Now if you check this, if I may squeeze it in down here, this is just pi over 2. Sine inverse of 1 is pi over 2, minus sine inverse of minus 1 is minus pi over 2. What are we saying? We have pi over 2 plus pi over 2, and our final solution is pi. That's the final solution to this integral here. There it is. Looking very intimidating, but as you can see, using trig substitution and a bit of algebra, we're able to obtain a very nice solution, the magic pi. All right, tell me what you think about this integral. Your feedback remains very critical for us. See you in the next one.